This will be the first video from chapter 3 in our text, in our online text, probability and statistics. And it's a very short chapter, and we're just going to do kind of two pieces of it here. So it's not going to take us long. Before we start, though, I put this screen on just to remind me, to remind you, that you should always be checking your grade. You can go into Skyward like you always have in other trimesters and check your grades, see if you're missing any work. So make sure that you're continually doing that. Well, what we're thinking about in this next chapter now is expectation. What would you expect in a certain situation? And I put these pictures here, just especially. I'm I'm wondering over here in the upper right. What about these people? I don't know what they expect. I definitely wouldn't sit there. If we think about where we've been so far, we started out here learning how to count and determine the sample size of the sample space. And we counted with 3 different counting methods. And then we moved into actually calculating probabilities. And that's where we graduated from simple to compound events, and we even worked with probability trees and those conditional probabilities. What's the probability of A, assuming B has already occurred? So we've been on quite a journey already, and now we're going to move into our expected value and simulation chapter. And we're going to kind of combine these two things together. So I mentioned before, we're going to pick up 2 parts of the chapter, and that's it right there. So Unit 3, expected value. And so in this first lesson, 3.1, the authors of the text are going to give us a formula, or basically it's a formula to determine mathematically expected value. I have a whole bunch of screens here that I might zip through really fast, but again, we're thinking about what would you expect? Would you pay the 20 bucks in this case? You never know, you could win the mystery meat package. I don't know what this person is expecting, but it's not going to be good. When we talk about expected value, the first thing that pops into my mind is insurance. Different places in our lives where we want to buy insurance, or we by law have to have insurance, like driving. You have to have car insurance. If you own a mortgage on a home, you have to have homeowners insurance. But there's a lot of other situations where insurance is optional. And then it's a, it's a situation where you have to analyze the scenario and decide whether you think it's worth it or not based on what you would expect. One situation where I always struggle is those extended warranty type things. Or even most recently, I just purchased a phone not too long ago because I accidentally fell in a hole of water out in the woods, and I ruined my phone. And I had to go buy a new phone. And I went to T-Mobile to buy a new phone. What phone to buy? I ended up buying a Samsung Tel, and it's their E version, Samsung 10E. It's super nice, but it doesn't have some of the bells and whistles of some of the other ones. Well, after agonizing over that, I went up to the register and they asked me if I wanted to buy insurance on the phone, if I wanted to insure it for breakage or loss. And oh my gosh, then I had another huge decision. And as it turns out, for the first time in my life, I have insurance on my phone. It's expensive though. Well, in these next few screens, I'm going to skip over a few things because normally when we're really meeting in class, we would perform a couple of experiments. And I'm gonna waive that for you guys right now. One of the experiments we do is based on this game that you see in front of you right now. And in that game, it costs you $1 to play the game. And in order to play the game, all you do is roll that great big red die. And when you roll it, if you roll an even number, you just lose your dollar that it costs you to play. But if you roll a 1 or a 3 or a 5, you win either 1, 3, or $5. So the reason I use this to introduce this lesson is, think about it. Would you want to play? Would you expect to win if you played? I would assume if you didn't expect to win, you probably wouldn't play, right? Well, there's a way we can mathematically analyze this to determine what we would expect to have happen, and we'll be doing that. The other experiment that we normally do, and I'm going to skip ahead, was this scenario where there's a second game and it costs you 50 cents to play. So you give me 2 quarters and then you toss a coin and you toss it twice. And the way the game works is this. If both times the coin lands heads up, you win $2. So if the result was heads and heads, you win $2. Any other result, you just lose the 50 cents. So again, when you think about the game, would you expect to win or lose? So to try to answer those questions, would you expect to win or lose? We formally have done an experiment, and we're gonna skip that right now. But we'll come back and visit those 2 games in our discussion now. So chapter 3, expected value. That's the key concept here, expected value. And if you're on page 77 of your text, your online text, there's 3 objectives. Here's the first one: be able to construct a probability model. And all that means is organize yourself in a table and then perform the analysis. Secondly, be able to calculate the expected value. And then the third objective is maybe the most difficult part, and that is to be able to calculate missing values in the model. So maybe the most important part of the lesson is the definition of expected value. You can see it's on page 78 right here in the online text. And on page 78, I'm just going to highlight it here as I do the presentation. It says the expected value for a situation can be thought of as the average result over the long run. The average result over the long run. So that's our definition for expected value, the average result over the long run. So thinking back to those games, if you played and played and played and played and played the game for a long time, would you expect to be way in the hole and have lost a lot of money? Do you think it would be break even? Do you think you'd be making a whole bunch of money? And so again, I'm skipping through some of these screens, but on page 79, they give us a formula, and in the book, it just says EV, but EV stands for expected value. And then what does that mean? As I mentioned already. Now, in your text, the formula looks like this, and I think that's really messy. And so if you're copying this into your notes right now, I would copy this formula instead. EV, expected value, equals probability times value plus probability times value plus probability times value, and so on. So the P's are probability, B's are value. You can see a definition here. Again, well, not really a definition, but the formula in words. I wouldn't worry about that too much right now. just remember PV plus PV plus PV like you see here, and then you're good to go. PV plus PV plus PV. Now, let's go back to that game where we roll the dice. And it cost you $1 to play, and then I'm going to write that here because I didn't put that on the screen. It cost, let's eliminate that, it cost $1 every time you play the game. I had put this here before because in our experiment, we played 30 times. So it cost us $1. Now, using that expected value formula, I'm going to put 6 of those PV terms here, and I'm going to try to speed it up a little bit. 6 of these PV terms, because when I roll a die, I could either get a 1, 2, 3, 4, 5, or a 6. And so I need 1 PV term for each possible outcome. There's 6 possible outcomes. I need 6 PVs. So now we ask ourselves, what's the probability of rolling a 1? Well, I got a 1 out of 6 chance of rolling a 1. And in the game, the value for rolling a 1 is I win $1. So I'm going to put a 1 for $1. Plus, what's the probability of rolling a 2? Well, that's 1 out of 6 again, right? And in this game, a 2 is even, and I win 0. I win nothing. And then I just continue. 1 out of 6 chance of rolling a 3. A 3 wins 3. 1 out of 6 chance of rolling a 4, which is worth nothing because it's even. 1 out of 6 chance of rolling a 5, which is the best thing you could possibly do because you could win $5. And then finally, the even 6 is worth 0. Now, if we add all of this together, the formula says we'll know what the expected value is. Well, 1/6 times 1 is 1. 1/6. This second term is just a 0. So now 1/6 times 3 is 3/6. Then we have another 0 term. 1/6 times 5 is 5/6. And then we have another 0 term. So I guess I don't need a plus. So it simplifies to that. And 1 plus 3 plus 5 is 9/6. 9/6 is 1.5. Now we're talking about money, right? So the expected value when you play the game is that you will, on average, remember the definition, average result over the long run? On average, you'd win $1.50 as you play the game. Now, if we also factor in knowing that we have to play it, cost $1 to play every time, if we subtract away the cost to play, in essence, it really means that as we play and play and play and play, we'd expect to make a 50-cent profit. The odds are in your favor. You're actually expected to win a little bit as you play. Now, it's random, so when you play, you could lose a whole bunch of times and win a whole bunch of times, but the average result over the long run, profit of 50 cents. The second game that we played or talked about, and we didn't really do the experiment, was if you got both coins land heads up, you win $2. Well, think about that scenario. When you toss a coin twice, it could have been heads and heads and you would have won, but you could have got heads and tails and lost. Tails and heads you would have lost, and tails and tails you would have lost. And so in this scenario, this was worth $2, right? $2 if you got heads and heads, but all of these things are worth nothing. You lose, they're worth 0. So if I use my expected value formula here, I'm actually going to do 1 probability and a value for winning and 1 probability and a value for losing. And so the probability of winning, this will be my win, this will be my loss. So the probability of winning, look at that, only 1 out of these 4 ways of playing do I win? So I got a 1 out of 4 chance of winning, and a win is worth $2. And three out of these 4 outcomes I lose. So I got a 3 out of 4 chance of losing and winning nothing. So if I simplify this, one fourth of $2 is 50 cents, right? And this is just 0. And so by using my formula, I get an expected value of 50 cents. And in that game, it cost us 50 cents to play. So if we subtract away the cost, we actually end up with 0 as our expected value. Which means the average result over the long run is that you expect to break. This is called a mathematically fair game. In the world of mathematics, mathematically fair means a break-even game. So here's our formula, expected value, PV plus PV plus PV. And that's the one you're going to use in your assignment. We could apply it here in one more example real quick in the video. Here's a game where you spin the spinner and the arrow rotates around, and here's the payouts. So, and don't forget, it's going to cost us $2 to spin. So let's put the $2 to spin off to the side for now, and we'll factor that in later. I'm going to need 4 PVs because I could spin and get any one of these 4 colors. So I'm going to go right down the line: blue, red, purple, yellow. So the probability of spinning and getting blue, I got a 1 out of 8 chance. Do you see that in the spinner? I've got a 1 out of 8 chance of spinning and getting blue, and that's worth $10. And then red, well, I got 2 out of 8. 2 eighths, which is 1/4. But I'm going to leave it as 2 eighths because I'm going to have to add, and I want a common denominator. So when I get blue, red, I get $2. Now I'm going down to purple. The probability I get purple is 3 out of 8, and purple is worth 0. And then finally yellow. So I'm just going to write it here. 2 out of 8 chance of getting yellow, and yellow's worth $1. So now I simplify this. Well, 10 times 1 is 10 over 8, plus 2 times 2 is 4 over 8, plus 0, right? I'm just gonna drop that off. That's 0. And then 1 times 2 is 2 over 8. And I have a common denominator of 8. And let's just add on the top. 10, 4, and 2 is 16. 16 eighths. Well, what's 16 eighths equal? And that's exactly $2, right? So my expected value is that I would win $2 on average as I play the game. Now that's an average. Sometimes I'd win 10, sometimes I'd win 2, sometimes I'd win 0, sometimes 1. But on average, I'd win $2. Now, finally, if we factor in the cost to play the game, which is $2, again, this is an example of a game where it's a break-even scenario, where it's neutral. I'd expect to win 2, but if you factor in the cost to play, it becomes a break-even game. Now, I'm going to skip ahead to your assignment. And, I almost forgot. We better not skip this. Hey, the nice thing about the expected value formula is that you've got algebra skills. You have got algebra skills. And I know then that in this equation, you can solve and get the expected value because you just type all of this into your calculator, right? And then you'd have your answer. But I'm expecting you can also do this. Everything is known except one of those values. It looks to me like there's a 60% chance of winning $5, a 30% chance of winning something, I don't know what the value is, and a 10% chance of winning $15. Well, this is where you'd show off your algebra skills and say, okay, 0.6 times 5, that's $3, plus 0.30 times V, I don't know what V is, so I'm going to leave it in my equation, plus 0.1 times 15 is 150. Now, can you solve that equation for V? If it was me, I would combine the 3 and the 1.5 and say 1650 equals 450 plus 0.30V. And then I'm guessing most of you would probably subtract the 450 from each side of the equation. And now we get $12 equals 0.30V. Now, how do we undo the multiplication there? 0.30 times V. Well, to undo multiplication, you divide, right? So you divide by 0.3, and I get V equals 0.3 over 0.3 is 1, and I've got to go to my calculator here. I'll turn it on, that helps. 12 divided by 0.3 is 4D, 4D. So I end up with a value, V, the value is 40. I think there was a 30% chance of winning a prize worth $40. Okay, so I'm gonna skip some screens. Sorry. By the way, there's really good examples in the textbook, in the reading from lesson 3.1. So this is the assignment that I'm going to ask you to work on, 1 through 6 and 8 through, 1 through 6 and 8 and 10. And this is lesson 3.1, an expected value. I'm sorry I didn't put a page number here. It must be somewhere around page 80. Oh man, I thought I had the exercises on here too. But I'm gonna stop this video right now and then add just another little video clip to show you how to get started on your assignment. So when you're done watching this one, open that other little video and I'll show you how to get going on 1 through 6 and 8 through 10. Excuse me, let me try that again. Through 1 through 6 and 8 and 10.